This is Dr.D Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. In this sessions, we are covering the topic of determination of centroid for the simple objects. Now, center of gravity of a plane figure by using method of movements. Here, center of gravity is treated as a point at which the entire weight of the object assumed to be passing through it. It is related to the three-dimensional object. If it is a two-dimensional object or the plane figure, the center of gravity is referred as centroid. It is the point at which the total area of the plane assumed to be concentrated at that point. The position of the centroid can be determined by using method of movements or Varignon's principle. Here consider a body which is represented its positions with respect to the xy plane. Assume the body is divided into several elementary points. Each are represented as M1, M2, M3, M4 and etc. such that the total mass of the body is given by sum of all the elements, that is M1, M2, M3 and so on. Let the position of the elements M1, M2, M3 are represented by using the coordinates x1, y1, x2, y2, x3, y3 and etc. with respect to the coordinate axis, which are represented as x-axis and y-axis. Let xc and yc is representing the position of the centroid with respect to the y-axis and x-axis. Then, according to the Varignon principle, the moments created by the component of forces is always equal to the, according to the Varignon principle, the sum of the moments created by the component of forces is always equal to the resultant of the moments created by the resultant. According to the Varignon principle, the moment created by the component of forces at a given point is equal to the moment created by its resultant at that point. Since the forces are treated as M1 into G, M2 into G, M3 G, all are perpendicular to the surface of the earth, and Mg is representing total weight of the body. Hence, according to the Varignon principle, M into G into xc, that is the total weight multiplied by the xc, that is the moment created by the body with respect to the y-axis, is equal to the M1 into G into x1, M2 into G into x2, M3 G x3 and so on. Since the word G is a common now, it can be written as mxc plus M1 x1 plus M2 x2 plus M3 x3 and etc. This M1 x1 plus M2 x2 plus M3 x3 is equal to the sigma mx I, where I is equal to 0, 1 to infinity numbers. So, the sigma of M1 plus M2 plus M3 is equal to total mass of the body, which is represented as capital M. Hence, the simplified equation for xc is equal to sigma xx divided by m now. Similarly, yc, that is the coordinate of center of gravity with respect to the x-axis is given by yc, which is equal to sigma my divided by m, where m is representing total mass of the body, which is equal to sum of the components such as M1, M2, M3. Now, the XC is given by sigma mx divided by capital M. Since the mass is nothing but now centered for the two-dimensional body. The same object, assume if it is having uniform thickness, the modified equation for the determination of centroid is given by xc is equal to m1 x1 plus m2 x2 plus m3 x3 divided by m. It can be written as rho into t, that rho is representing density of the material, t is the thickness of the materials or the objects, into a1 is representing the area of that particle that considered, into x1 plus rho t a2 x2 plus rho t a3 x3 divided by total mass, again it is given by rho t into a now. Or in other words, since rho t is the common word for in denominator and numerator, hence it can be written as sigma ax divided by a. Similarly, for yc, the y coordinate of the centroid is given by sigma y divided by a now. These are the equations generally used for determination of centroid for the two-dimensional body. Similarly, in order to locate the centroid of one-dimensional body, let us consider uniform y, having the cross section is remains constant. Assume that entire length is divided into infinite number of elements, such as each as having L1, L2, L3 and so on. So the total length of the object is given by L is equal to L1 plus L2 plus L3 and so on. So the modified equation for determination of center of gravity is already discussed as xc is equal to m1 x1 plus m2 x2 plus m3 x3 divided by total mass of the body, capital M, where m1 stands for rho and a is the constant now, rho a, as t here converted as L1, hence it is modified as rho into a into L1 into x1. Similarly, rho t, rho a L2 x2, similarly rho t, rho a L3 x3 divided by rho a L. It can be written as, since the area of the cross section remains constant and the density is also constant, so the modified equation for xc is given by L1 x1 plus L2 x2 plus L3 x3 divided by L1 plus L2 plus L3 and so on, which is equal to total length of the body. Or simply xc is equal to sigma of Lx divided by L. Similarly, yc is given by sigma Ly divided by L, where L stands for the total length of the body. For some of the bodies, it may be irregular. In that case, the position of center of gravity or centroid can be determined by using integration method. According to the method of moments, the center of gravity is given by xc is equal to sigma mx divided by sigma m. Since the body is not divided into infinite number of infinitesimal elements, hence the modified equation can be written as integration of x dm divided by integration of dm. Similarly, yc is equal to that integration of y dm divided by integration of dm. Centroid of two-dimensional body, according to the integration method, x is given by integration of x dA divided by integration of dA. Similarly, yc is given by sigma ay divided by sigma a, which is equal to integration of y dA divided by integration of dA. The centroid of one-dimensional objects, according to the integration method, xc is equal to integration of x dl divided by integration of dl. Similarly, yc is equal to integration of y dl divided by integration of dl. Now the position of centroid for the plane figure, here rectangle we are considering. It is a two-dimensional object, or the object which is having uniform thickness. Let ABCD is representing a rectangle having breadth is equal to B and depth is represented as D. Now consider steep PQ, which is at a distance of y below the symmetrical lines, which is represented as x and x in a given. Now, in order to determine the position of centroid by using moments method, we are considering a strip which is at a distance of y, having infinitesimal thickness dy. Then the area of the strip PQ is given by B into dy. Now, according to the method of moments, the position of the centroid is given by C. It is equal to integration of y dy divided by integration of dA, and that integration should be done within the limits d by 2 minus d by 2. Hence, on doing yc is equal to minus d by 2 to d by 2. B dy is representing the area of the strip into y, that is sigma day integration of y dA divided by integration of dA. Now, by using this equation, we got it is equal to d by 2 now. Similarly, the position of the centroid with respect to the extreme position is given by b by 2. Hence, the position of the centroid for the rectangular plane figure, it is the intersection of symmetrical lines. Now, the position of the centroid for the triangular figure. Let ABC is representing the plane figure, or a three-dimensional objects having uniform thickness. Let B is representing the base of the triangle, and height is representing as H now. In order to determine the position of the centroid by using integration method, let us consider a small strip EF parallel to the base BC at a distance of y as shown in figure. Now, according to the geometrical construction, the triangle ABC and triangle AEF both are treated as similar triangles. Hence, EF divided by BC is equal to H minus Y divided by H, or EF is equal to B into H minus Y divided by H. You got it now. That is representing the length of the assumed element EF. The area of the strip is equal given by EF into dy, where dy is representing the thickness of the element. Now area is given by EF into dy, which is equal to B into h minus y divided by h into dy. Now the center of gravity of the tip above the x-axis or with respect to the base BC is given by, according to the integration method, sigma y dA divided by sigma dA. Hence, B into h minus y by h into y into dy divided by B into h minus y by h into dy. Since B and h both are constant that are eliminated from denominator and numerator, the final equation now becomes h minus y into y dy divided by h minus y dy, which is equal to hy dy minus y square dy divided by h minus y dy. Now, the center of gravity of the entire figure is obtained by integrating above the equations from the 0 to h. We got the relations of xc is equal to, so yc is equal to 0 to h, integration of 0 to h minus y minus y square dy divided by integration of h minus y into dy. On simplifications, we got h y square by 2 minus y cube by 3 divided by hy minus y square by 2. On integrations, we got h y square by 2 minus y square by y cube by 3 within the limits 0 to h divided by hy minus y square by 2. On applying limits at a place y position, we got 3h cube minus 2h cube by 6 divided by h square minus h square by 2. Finally, we got it is equal to 1 by 3h. That means the position of the centroid lies at a distance of 1/3 of its side from its base position. This is the conclusion. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.